Okay. So, let us come back and continue with the implicit function theorem. So, what we observed that we could achieve our goal to have every level curve locally as a graph, that if I have this for every fixed x in this neighborhood, what we have to decide, I can have a neighborhood of y such that y going to f x y, this function, this has a 0 here. A 0 here means it changes sign at the two endpoints, and the uniqueness will be guaranteed if this is strictly increasing. This is one of the sufficient conditions. There could be many, but we have to attack whatever we have in position. So, if it is strictly decreasing or strictly increasing, then I will have unique 0. And what does it mean by strictly decreasing or strictly increasing? That means I should have del f x. So, I should have d f x dy, this is greater than 0 or strictly less than 0, here is strictly increasing or strictly decreasing for each fixed x in this interval. So, that is to say, in terms of f, del f del y x y is strictly greater than 0 or strictly less than 0 for x y in the interval you have decided. Okay. Well, what we are trying to do, given each x in this interval, we are trying to find a unique y. This is a sufficient condition. You understand very well that okay, we could have, instead of defining function of x, we could define function of y, that we will also do. So, the role of x and y could be interchanged, that first so depending on the situation, that suppose I do not achieve this, but I have del f del x x y is greater than 0 in some interval, and for fixed y f x y changes sign in the interval of x naught minus epsilon to x naught plus epsilon, then I could have achieved this. So, this is for writing function of x. So, instead of that we could try to write function of y as well. So, role of x and y could be interchanged. So, what we actually need here is that the conclusion is that I need one of this, either del f del x or del f del y at x y in this interval is non-zero, or x naught y naught at x naught y naught point non-zero, and del f del x del f del y continuous at x naught y naught. Then what will happen? It is non-zero, so one of them is non-zero. So, let us say positive or negative. If it is positive or negative and continuous, then I can decide an interval around where it remains the same sign. Okay. So, I need continuous partial derivative of f and del f del x del f del y at that point non-zero. Now, if you look at it geometrically, that is a very nice interpretation. So, this fellow is what? This fellow according to our notation is grad f x naught y naught. Now, what does x naught y naught belongs? This belongs to this level curve f x y equal to some constant, okay, f x y equal to 0. If I have a level curve, let us say this, and if I fix a point x naught y naught here, then this you can check very easy that this fellow, this is precisely the normal at x naught y naught. For a level curve, grad at some point is the geometrically is the normal to that point. And this condition means normal is non-zero. Normal non-zero means it is not parallel to x axis. Okay. So, this condition grad f x naught y naught, or let us say n not equal to 0, that is n is not parallel to x axis. This is what geometrically the condition we are imposing, and what it means, and also the normal is changing continuously. Now, if normal is not parallel to x axis, why we achieve it? You forget everything else. If I have this curve and normal is not parallel to x axis, then the tangent, this is not parallel to y axis, because normal and parallel tangents are perpendicular to each other. If at a point tangent is not parallel to y axis, what does it mean? If I move little bit from here, this side or this side, and fix the x here, so let us say x naught plus something, some little bit of I move from x naught. So, in that neighborhood I have to decide. Then if I draw this line, this is the line x equal to x naught plus delta x, then this line will intersect the curve at a unique point. Similarly here, x naught minus delta x. So, this line x naught minus delta x, y equal to x naught minus delta x, so this line, this will intersect this curve at a unique point, and that is my unique y. That is what we are looking at. So, geometrically that is it, what is going on, and it is very, therefore, I said it is very easy to understand in function of two variable taking values in R. What we all demand is normal exist non parallel to x axis and it is moving continuously. If I have that, we have it. And of course, you can see that instead of this, why we cannot achieve it everywhere? Why I need this? Suppose I have a picture like this, and I am looking at this point x naught. This normal is outward normal this way. So, tangent is this line itself. Now, if I move from x naught, moving this side does not make sense because there is no power portion of the curve. If I move this side, any point you move, you will always have 2 points on the curve. So, you cannot decide y uniquely. So, that is the geometry of implicit function theorem. Now, I hope we understood what is needed. Once we understood, we just put them whatever we need as assumption and prove the theorem. So, let me state implicit function theorem for function of two variable. For f from R2 to R. So, when you state your theorem and prove a theorem, you have to do it carefully. So far what we have been doing informally whatever we need. So, we put it formally now. So, let us put the setup, let U in R2 be an open set. f from u to r okay, and x naught y naught belongs to u. So, suppose f has continuous partial derivative del f del x del f del y at x naught y naught, and of course, x naught y naught is on the level curve equal to 0. Then there exist a epsilon greater than 0 and a neighborhood let us say theta of x naught y naught and a function g from x naught minus epsilon to x naught plus epsilon to r such that what happens? 1 fx gx equal to 0 for all x in x in x naught minus epsilon to x naught plus epsilon, g of x belongs to theta, and of course, g of x naught equal to y naught. This is what we wanted to achieve, but we can actually achieve something more. What? That of course, what we achieve, what we are going to write is much desirable, because we have taken f is very nice, it is continuously differentiable, it is a C1 function, it has continuous partial derivative. So, f is a smooth level curve, whatever we have now defined what is smooth curve, but you understand in layman's term that f is nice is a nice function of two variable. And so, we will also get g is differentiable. In the entire interval. So, this is the statement of implicit function theorem from R2 to R. Let us understand it. So, and remember it for R2 to R. From here, the general statement is just mere formalities. So, this part is not really needed in the statement, but it is actually part of the proof. It is a part of the proof. I have just included it. This is not needed in the statement. Just for whatever the question is answered here without this statement, this neighborhood. But the way I have presented it, I mean, we have motivated ourselves. Actually, this will be true. This theta will come, and what will happen is, what this two statement means, that actually that there exists a differentiable g such that f inverse of 0 intersection theta, so this is the local part, equal to x g x x in x naught minus epsilon x naught plus epsilon. So, this part of the curve is the graph of this function. Okay. Now, we actually know how to prove it, because we have actually made this statement in the other way around, that we have actually put the assumption what actually we needed, but still we need to write down the proof formally. So, we know all the assumption. This continuity is needed at x naught y naught to maintain the same sign of del f del x or del f del y. So that in a neighborhood, if for a fixed x, f x y is strictly increasing or strictly decreasing function of y, and non-zero. Oh, I have not put this assumption this way, somehow I missed one assumption, right. Quadrature partial derivative, and most important assumption, let us assume del f del y at x naught y naught, sorry, this is greater than 0 or less than 0, does not matter, but this was our part of assumption that we need a normal. So, this is the actual statement. Okay. So, you need, so since this is greater than 0, it will maintain, continuity will tell you that it will maintain the same sign, and we know how to actually go about it. So, let us write down the proof formally. What is the step 1? Well, what we do, I have del f del x del y x naught y naught is bigger than 0. So, I can choose a closed interval. I can choose an open interval first, and then inside that I can choose a closed interval. You will see why I need closed interval, such that del f del y at x y is, let us say, bigger than some number b, okay, for all closed interval, give it a name, choose this interval, what do you call it, how do you call it, d, small b here, for all x y in d. This is why continuity, and del f del x x y is less than some number a for all x y in d. It is a continuous function del f del x in a closed interval. So, it will have a maxima and minima. So, I check the maximum, and there I take the minimum. Okay. Okay. So, let us look at f of x naught y naught minus delta minus f of x naught y naught, and apply MBT. MBT for y naught, x naught is fixed. So, MBT in y naught variable. What is it? This is equal to how much? Del f del x at some point x naught y 1 into okay, I can apply MBT to any x, okay. Okay, not x naught. So, x minus x naught plus del f del y at x1 y1 into y naught minus delta minus y naught, that is minus delta, okay, for x in this interval x naught minus delta, x naught plus delta. Now, what is f x naught y naught? This is 0. So, left hand side is just this fellow f of x naught y naught delta. Okay. Now, what I will do? I will make this delta, I will choose a smaller interval. So, epsilon is less than, which epsilon? Epsilon is less than delta, such that I still have del f del x is less than a, and I will also make epsilon minimum of b delta by b delta by a. Then if you look at this fellow is less than a epsilon less than equal to a epsilon, strictly less than a epsilon minus b delta, and this will be strictly less than 0. It is less than equal to here doesn't less than, yeah, this is strictly less than. So, what it says? This says f of x y naught minus delta is less than 0. So, I can apply MBT for each x in x naught minus delta to x naught plus delta, but I make smaller interval such that I get f x for x in the smaller interval x naught plus minus epsilon, x naught plus epsilon, epsilon is less than delta and less than this fellow such that this is less than 0. Now, a similar calculation. So, this x1 y1 you know why I get x1 y1 is it? Is in the line joining. X y naught minus delta and x naught y naught. So, I have to play this trick, I have to string the interval here. Now, what I do? So, similar calculation will show, it will follow that f of x y naught plus delta, this will be bigger than 0 for x in x naught minus epsilon, x naught plus epsilon. So, plus delta bigger than 0, find f of x minus delta bigger than 0. So, therefore, there exists a unique why unique? Because for fixed x is x naught minus epsilon, x naught plus epsilon, if x f of x y is strictly increasing. This is implied by del f del x, del f del y bigger than 0. There exists a unique y in the open interval y naught plus minus delta y naught plus delta such that f of x y equal to 0. So, I define g of x equal to this y, x in this interval. So, I got this interval. So, I got a definition of g. Only thing remains to prove is differentiability of g. But for differentiability, first we will show continuity and then differentiability, I mean both will come. Okay. So, I got the first part right. Second part, differentiability. Of g. Well, let us check x1 and x2 in this interval, and let us put y1 equal to g of x1, y2 equal to g of x2. Okay. Now, look at this fellow f of x1 y1 minus f of x2 y2. What is that? Both of them are on the level surface. So, this is 0, this is 0. So, this is 0 equal to, I apply MBT again, del f del x as some x3 y3 at x1 minus x2, okay, plus del f del y at some x3 y3 at y1 minus y2. Again same thing, I have to write x3 y3 in the line joining x1 y1 and x2 y2. What does it say? This side is 0, this fellow is less than a. So, this will say g of x1 minus g of x2, which is equal to y1 minus y2, bring everything to this side, is equal to minus del f del x x3 y3 divided by del f del y x3 y3 x1 x2. Take mod here, okay, keep it. This fellow is less than a, this is greater than b. So, 1 upon this is less than b. This of course implies G is continuous, right. And just for differentiability, u from star, it also implies g of x1 minus g of x2 divided by x1 minus x2 equal to minus del f del x at x3 y3 del f del y x3 y3. Okay. So, suppose x1 goes to x2 now, I take limit x1 goes to x2 or x2 goes to x1, let us say. What will happen? Limit x2 goes to x1, left hand side which is actually derivative of g of x1. This is equal to x1 goes to x2, x3 y3 is in the line joining x1 x2. So, x3 y3 will also collapse to x1 x2. So, this is minus del f del x x1 y1 by del f del y x1 y1. This is non-zero. So, this is exist and G is differentiable. Not only differentiable, we actually get what it is. It is minus del f del x x1 g x1 divided by del f del x x1 g x1. That is it. That is the proof of implicit function theorem.